computations. And so last time I computed some potential function for torus fibers or toric manifolds, and then somehow I used iterated integrals. And probably I don't really need to tell the whole story, but maybe just for maybe somebody may be interested in this, so therefore I just tell you this story. So this is a story somehow developed by Chen, maybe 70s or, and so this is the following. So let X be a manifold. And then maybe we may be interested in path space. Or maybe loop space. And then try to consider some drum theory over here. And so this one is the following. What is the differential forms? On such spaces. Or maybe this space. Right. So this is infinite dimensional space. And yeah, if you consider certain condition like a continuous path or maybe smooth path, and then you may have a chart. But anyway, so differential form is actually usually the cross-section certain vector bundle which is obtained from the exterior power of the tangent bundle. But it is infinite dimensional, so therefore it is not so straightforward to do this. So instead, some people understood differential forms in the following way. So let's suppose that you have some map like this, right? Say this. So this is a manifold, certain finite dimensional manifold. And target is this path space. Maybe I denote by phi. And then for each such smooth mapping, mapping, maybe if you have a differential form here, then if you just imagine that you have some differential form here, and then you may prove back it by this. So therefore, you may have a differential form like this. Right? So for any such things, you may get this if you have a differential form on the loops on this infinite dimensional space. But then we need some condition, right? So you have a V here. If V here, and then map into U by certain smooth map, and then go into this space by this. And then certainly you also have a map directly going from V to Px by just do phi composed with F. Right? So then the condition is the following. So certainly if you have a differential form here, differential form here, you can put it back here, then you can pull back the differential form here. This is usual pullback, right? It's a finite dimensional manifolds. So therefore, they must related by this pullback, right? So somehow we consider collection of forms on the domain of such a mapping, and then maybe I just put this domain be phi, and then here you have phi here, and then here phi, and then maybe this better to write a U of phi composed with F. And then you have this. So we may just consider such a collection. I mean, the element here is a collection of differential form on such domain of mapping phi with this property. So maybe we can think of it as a kind of differential form on this space, right? Say. So if you want to consider P form, then everything is P form, and then here you have P form. Something like this. Right? And then you can easily define analog of exterior derivative and wedge product. So D, because you have a correction, right? So this omega phi, so that f omega phi is equal to omega phi composed with f, right? And then this one is mapped to this D of omega phi. Certainly, this one implies that f star of D of omega phi is equal to D of omega phi composed with f, right? So you have this, and also you have exterior product, like you have two things like omega phi and eta phi. Then you can think of this omega phi with eta phi. And certainly if f star of omega phi is equal to omega phi composed with f, and f star of omega eta, omega phi, eta phi is equal to eta of phi composed with f, then you have certainly the condition that pullback of omega phi with eta phi is equal to omega phi composed with f with eta phi composed with f. So therefore you have such a kind of drum complex. And so the iterated integral is the following things. So anyway, we have a space X, right? This is manifold X. And from the information on X, you want to get some information on this associated space, like path space, or loop space, and so on. And this construction is very similar to our MK operator. In fact, we are partly inspired by this construction. So the idea is the following. So I have a path space Px, say. So this is a path, space of paths. So therefore, this one is space of paths. So therefore, this gamma is mapping from 0, 1 to x. Maybe I assume smoothness or something, but just to write in this way. And then I have a map. Also, I denote by delta k. So this one is a simplex, like a T1 Tk in this 0, 1 to the power k. So they are monotonically increasing. Like this. Then we have a map to this. And then I have a map to this Px. Maybe I only consider a case that I have a base point something. Yeah, I have a base point here, maybe x0 or something. So the starting point may be fixed. And then we have this diagram. Namely here, if you have here this T1 Tk and gamma and then I just map it to gamma T1, gamma Tk, right? And this one is just forgetting T's, so just map it to this element gamma. Okay. So if you have a differential form here, then we want somehow you may try to put it back to this space and then push it out to this space. And how can you do this? Because we have this sort of framework. So therefore, instead of the path space itself, I just replace this space by this space and then do this. So here I consider this u phi from here to px. And then certainly we have delta k times u phi. And then here, again, this x, x. And then here, I have a map to this u phi, right? And so maybe I usually I denote it by F1, Fk. And so I want to also use the same notation here, like F1, Fk. But more precisely, actually, I may write in this way, but this one is eventually the composition of this thing, right? Okay. So just mapping this one to this one, and then take the values here. Right? So anyway, so this way. So now we are in this situation. And then you just put it back and push out. So this is iterative integral. So let's C1, Ck are just the differential forms on the manifold X. Then I just want to put it back to this space. So I have to give a name for this. Maybe this one is pushed out by projection to the second factor, but maybe I just like p phi. And then I consider this C1 tensor Ck is mapped to something, and that I just denote by this. This? This is just a symbol. So this integral, so far I don't really specify where I integrate because it's just a symbol. Because this element in this space. Okay. So this is actually in this. Sorry. So maybe I just use by this, and then this one is in this omega of the path space. So what does it mean? So it means, this one means that if you have this u phi to this space, then I have to assign some form, right? So I want to assign some form like C1, Ck phi or something. So now this one is a differential form in usual sense on this domain of this mapping phi. And this one I define as follows. So this is basically this p phi streak, and then here maybe I use this F1 composed with identify star. C1 with F K composed with identity phi of CK or something. So basically, I want to pull back differential form here, and then take the weight product, and then just take integration along fiber, along this. Okay. And then I want, so here I want to put some sign here, and this sign, at the first glance, you may think it may be a little bit strange, but this somehow we often encounter with. So this one is now k, so therefore here k minus 1 of degree of this form, degree of this differential form, plus 1, plus degree of psi k plus 1. So maybe I just introduce some notation. So maybe if I write ck, and this is just a degree of psi k as a differential form, and then I also have so-called shifted degree, and this one is equal to degree of ck, I think minus 1. Okay. So this one is actually the sum of k minus I of ci prime, and I runs from 1 to k. And I equal to k, I have nothing here.
I'm sorry, but the last term is degree of ck plus 1. So why does it?
K minus 1, sorry. Thank you. So actually, if you look at our book, you may have quite strange way of writing this. So we always write it in this way. So I is from 1 to k minus 1, and j is equal to 1 to I. And then here we take this degree of psi I plus psi j plus 1. So we wrote in this way. So this one is exactly the same as this one. Maybe, yeah. So if you look at this, and somehow, we found this sign by certain try and error, so therefore I come up with this, and I didn't really write in this way. But if you write it, and then, so if I equal to 1, what you have is degree. If I equal to 1, then you have here psi 1 plus 1, and then degree psi 2 plus 1, wait. So, yes, up to k minus 1, right? So degree psi k minus 1 plus 1. And then the second, if I equal to 2, and then I have, if I is equal to 2, sorry. I made some mistake. Sorry. If I equal to 1, sorry. I always have some difficulty with this. If I equal to 1, I have this. And I equal to 2, I have this. And I equal 3, I have 3 terms. And then in the end, I have this degree of psi 1 plus 1 plus this one, and up to degree psi k minus 1 plus 1. And so I have 1 to up to k minus 1. So therefore, here we have k minus 1, many of them. And here you have k minus 2, many of them, and so on. So therefore, this one is, in fact, this. So this is maybe better to write it this way. But if you look at a book, actually we always use this way. And sometimes even we put some n over here. But anyway. Okay. Sorry. This all minus 1. Sorry. Because we're only interested in a sign, so therefore plus 1, minus 1 doesn't matter. So for sign, it doesn't matter. But this is for degree, actually, I need to take minus 1. So this shift is somehow quite important because when we consider bounding cochain, we consider it, I started with an odd degree form, in particular 1 form, and then this one has degree 0. And so actually, yeah, this minus 1 is, if it is plus 1, then 1 form becomes the degree 2 in this new set. So that's it. So anyway, so this is the definition.
The sign doesn't depend on the CK?
It depends. CK, no. No.
Okay.
No.
And the last sum will depend on the CK?
Hmm? This is 0.
Oh, okay. It's 0.
And then if you somehow consider this thing, right? And then everything somehow behaves nicely. So I have this diagram, and I also a diagram for this, and then there is always some canonical mapping, and then integration of fiber gives you this. So this is one way maybe to construct some different form like this. So from different form on X, you can cook up some different form of the path space. And this integration along fiber is an iterated integral. Okay. And then next, I want to explain the special case. So let's suppose that C1, CK are all one form of these things. Maybe, yes, one form, yes. Let's suppose this. And also suppose that this Ci is actually exact one form. And in this case, we have the following. So, yes, integral of C1 Ci Ck, but this Ci is equal to this df, right? You just do this integration stuff, and then this one is equal to C1 Ci minus 1, then f times Xi I Ck. So here are k entries. So here are k entries, right? And here we have k minus 1 entries, because I just remove this Xi I, and then I just multiply f to this Xi I, and minus Xi1, Xi I minus 2, and then f times Xi I minus 1, and then Xi I plus 1, Xi k. This is also k minus 1 things. And yeah, this is the case when I is strictly between 1 and k, this one, sorry, I plus 1, thank you very much. I plus 1, yes. Yes, I plus 1, thank you very much. And when say, I is equal to 1, and then we have this thing similar to this, so similarly f psi 2 psi k minus f of maybe phi composed with a variation. Yes, phi composed with, no, a variation composed with phi. A variation composed, sorry. Yes, but maybe I have to say this. So here I have f1 to fk, but I also want to write f t equal to 0 of this thing is equal to gamma 0, and f t equal to 1 of this thing is equal to gamma 1. Okay? So 0 and 1 are endpoints, and then I just denote this endpoint as ft equal to 0 of gamma or ft equal to 1 of gamma. And so here I take this one, so f t equal to 0. Yes. And this psi 2 psi k. This is the case I equal to 1 and I equal to k. This one is equal to, sorry, this one is equal to, yes, f of evaluation t equal to 1 and psi 1 psi k minus 1 minus integral of psi 1 psi k minus 2, and then finally I multiply f to the last one psi k minus 1. Okay. So this is not so hard to see because we have zero to 1, and then I do this iterated integral. So iterated integral is certainly the following things. So this one is integral integral of dt1 dt2 dtk. So maybe I take an integral of dt t equal to maybe 0 to t2, and then integral from 0 to t3, and so on, right? No, sorry. No. This is opposite, because if in this case, which one is correct? So I want to consider this sort of integration, right? This is t1 and this is t2. So I have to integrate t2 first. Yes, t2 first, and then do this. Yes. Because this one is actually this side, right? No, it's okay. 0 to t2, 0 to t2. Okay, I think this is okay. And then 0 to tk. Something like this. Of some function. And so let's suppose that you have one thing like df of t I, right? So if you have one part that is something like a df. Sorry. Maybe it's not so easy to write it, but if I just use this, maybe something like this. If psi I is equal to df, no, sorry. Okay, so df dt of a ti, right? So you may have such a thing somewhere, and then you want to integrate this from t equal to t, from ti minus 1 to ti plus 1. And then what you get is f of ti plus 1 minus f of ti. Right? So here, one of the entries is actually exterior derivative of something. And then you just put it back and then restrict it to this part, one of the fibers. And then you do this sort of computation. And then if you integrate this thing with respect to ti, and then this is the value of f at ti plus 1 minus f at ti minus 1. And so, therefore, you just do this, and then you get this. Even checking signs. And why I wanted to say this? Because this one is somehow related to what I said last time. So last time I actually wanted to compute this thing, right? So B is the one form on this toric fiber or something, maybe lambda plus. But anyway, so for each power of t lambda I, yeah. So maybe here you have maybe psi I, something like this. So B may be written like this, and this one is just usual H1 of LU with complex coefficient, right? And so we just want to do this. But this one is actually the sum of this thing. And this thing. And they are one form. So therefore, shifted degree is actually 0. So therefore, no sign appearing here. So you just put it back and integrate. That is this one. And then, so at each fiber, we want to do the following. So I have. So this is a fiber. I mean, okay, sorry. So let's consider some map like this is a holomorphic map, and then we want to consider integration on fiber of this one, because here I have one more lot of map points Z1, Zk, and Z0. Right? So I have a one form here, and then I want to put it back, and then try to integrate it on this. So therefore, this one is a exact one form. No, closed one form, right? This is a closed one form on this circle, because this is a closed one form. So somehow I want to do this sort of integration. But the difference is that here I discuss the case that it's a path space. So path space, so therefore I have starting point and end point, right? I can also fix end point. And so then I have this. But here the integration is not for the path space but for the loop space, right? So loop space then certainly it is the domain is this, right? So then this one is the mapping like this. And so here, if you look at this, so if I have a closed one form U star of psi, and I only need to know its cohomology class. Namely, this is the closed form, so therefore this is equal to something like constant times d theta. So this is just a standard one form on this S1, and then multiply some number, and plus certain exact term. So therefore we can apply this. Because what we do is integration of maybe this c d theta plus dh dot c d theta plus dh. So we can actually use this kind of computation. And if you look at this, and sum them up over all position, right? Because this one may be the first position, second position, third position, therefore you can just do this. And then they exactly cancel out. And these two also cancel out because these two terms are the same, right, for loops. So therefore, what I want to say is that this computation, to do this computation, only the cohomology class of this pullback one form is necessary to compute this. So therefore, last time what I said is, if you do this, this is enough to compute. Because if you have this, and then this part doesn't really contribute, really doesn't matter what kind of exact form here. Only here, right? And then you just multiply c to the power k. And so therefore, the computation is actually only depends on cohomology, not really representative of these forms. So that's why I wanted to just mention this. So if in easy case, you know exactly what the pullback form is, so therefore it's okay. But if you consider non-Fano case, and then you may have a more complicated things, not really easy to see, but still, if you know the cohomology class, that is enough. So that is what I wanted to explain. But it's some sort of side remark. So this is quite nice, and only for these one forms. Now I just want to explain you a bit more about this. Because then you can also see some sort of actually we can see some sort of infinity structure, but coming from DGA. So DGA is actually, we have a drama algebra, so therefore we have DGA here. But okay. So what's next, right? So I explained a little bit about this. Maybe we can also talk about loop space, or maybe free loop space, or maybe. So here I put x0, and maybe here is a based loop space, and then maybe the free loop space. Anyway, you can do this sort of computation. But so here I have a map from omega dot x tensor k goes to omega dot of px x0. And let's look at the degrees, right? So here you have C1, Ck. So the degree is actually certainly this degree. How about this side? So here you have this C1, CK. What is the degree of this? So we put it back. Degree of this one is equal to degree of this one because put back preserves the degree. But then you integrate along fiber, the dimension of fiber is K. So therefore, the degree of this one is equal to C1 plus CK minus K. Okay. So therefore, this is actually sum of C1 prime plus psi K prime. So therefore, this shift is quite natural for if you consider. So this is one thing. So this is okay for anything. And so, but for free loop space, maybe we may also do the following. So maybe we may also do the following. So this is a free loop space. And then I may just put one more thing. So namely, here I have psi 0, and then psi 1, tensor psi k. And then maybe I just put it back by ft equal to 0 star of psi 0 and this one. So this can be done, right? You just put it back like this. But today I just forget this part, and I just discuss the rest of the things. When we consider free loop space, certainly the I don't know how to say, the image of 0 is certainly one of the information, so therefore this is the one. But so I want to tell you several propositions. And one is the following. So you just consider this psi 1, psi k. So this is a differential form on the loop space or path space. And then I already erased, but we can define exterior derivative and wedge product, right? So maybe you may wonder how it looks like. And then this one is equal to so I don't know whether I should really give you this sign or not, but in fact, without talking about sign, maybe it's not so, maybe sorry, plus 1. And I think if this is this, if it is this, and then that may be better. But I think that here we have plus 1. I forgot. Yes, maybe I need plus 1. And then psi 1, psi I, wedge psi I plus 1, psi k. Certainly I have to add them up. Sorry, I have to add them up. So here I could be 1 to n, 1 to k. And here I can be 1 to k minus 1. And here the entries are k entries here. And here we have only k minus 1 entries. And this is one proposition. So this side you take this exterior derivative, right? And then this side, you can find exterior derivative and also this wedge product. So this is one thing. And we can also talk about the wedge product. And this one is also maybe this one may be more easier to understand. So if you take a k plus L many differential form on X, and then take first k differential forms and apply this iterative integral to get the differential form of the loop space. And then you also consider the rest, I mean, the L differential forms, and then apply these iterated integrals and get another differential form of the loop space, and then take exterior product. And this one is actually equal to, so this is a sign of shuffle of shuffling Xc1, Xck, and Xck plus 1, Xck plus L, and Xc sigma 1, Xc sigma k, no, I don't know, maybe just Xc sigma k plus L. Shuffle means that the first 1 to k, certainly this sigma 1, sigma k, and sigma of k plus 1 is k plus L. But this one may be smaller than this, and so on. So you have two sets of things, and then you just put it in. And then here you have this psi sigma 1 dot psi sigma 2 psi sigma k plus L. So this is another thing. And so this one certainly, yeah, you may just easily imagine, because I have so one set like a T1, T2, Tk, and then I have another set like, maybe this is 0, but here I have S1, S2, SL. And then using iterative integrals, you can just do this. But you take a wedge product. That means you consider the product. Yeah, integral is taken over this product. Right? The fiber is this. I mean, this one is integration over this, and this one is integration over here. Now you just put them together. And then here you have 0 here. I don't know how they are located, but anyway, so T1 to Tk are respecting this cyclic ordering, and then S1 to SL also respecting ordering. So therefore, you have this stuff, right? And so this can be decomposed into certain simplices. Copy of the K plus L. And these copies, I mean this kind of types. And so then certainly you have to switch them. So therefore you need some signs here. So that's this sign. So anyway, so this is exterior derivative, and this is wedge product. So yeah, using this. So here actually I didn't really put this psi 0 one. Yeah. So therefore, if you really want to understand the topology of this, certainly this part is also quite important. But this is just a pullback, right? Pullback of this form to somewhere. And so therefore applying D, certainly use LD. And also wedge product, certainly you just take a wedge product, like here. Right? So that is not so hard. So anyway, so So we have kind of drum complex on the loop space, right? So we have a drum complex on this loop space, and we have a differential, and also this. And in good cases, like X is simply connected, then this one can compute the cohomology of the loop space, something like this. So this is actually I already erased, but maybe goes back to 10. And the weight product is certainly the product. And maybe I may come back to this, but for loop space we have other things. So therefore, sometime I just consider this based loop space. So for this based loop space, there is additional structure that is a concatenation of loops. So for this one, actually we have a concatenation of loops. And then how you can see this. So if I take here alpha and I have here beta, and then here you have this alpha composed with beta. So first you travel along alpha and then followed by loop beta. And then maybe I just consider some function part. Other part actually I didn't really check. But then if you want to consider this psi1, psi k, and then consider value at alpha beta, and then it actually decomposed into two. Of alpha, and then integral of. So this is additional things. And certainly summation maybe must be taken over I may be even 0, or I may be k, right? Because you have a parameterization of the loop. So here I have 0, and maybe T1 and T2, and so on, right? So they are just points on the circle so that they respect cyclic ordering. So if my path that is alpha and beta are somehow parameterized by the half, I mean just this half of the circle, and this one is another. This one is this one is already. This one is actually beta. And then, so how this T1, Tk actually located in here? So certainly they are actually decomposed in two groups. One is corresponding to this upper circle, and then the rest is actually lower circle. Right? And so therefore you have this. And so you can just actually see something. And when you, if you know or you're interested in so-called string topology stuff, and then not only this based loop space, but the free loop spaces, they may meet somewhere, and then you can do something, right? And so such operation, maybe also can make sense in this But then you need a intersection theory of this. And that is actually not so easy to carry out in this level. But yeah, there is say, for instance, the work by K.E.D., and he actually studied the string topology using kind of drum homology model or something. Combination of this sort of idea of differential form and virtual technique, the Kranich structures. So anyway, so this is actually not today, this time actually I didn't really say this. And but what I want to mention is this thing. So this is actually very nice story. And probably too much to really explain the science, and so I just. But actually, this is actually the consequence of what I explained last time. This you have M, and you have B, P, and also you have a boundary of this and this. And if P and this are both submersions, then d p streak of say xi is equal to -1 to the dimension of fiber of p streak of d xi plus -1 to the dimension of this fiber p times p restricted to m take streak and xi restricted to this. So this formula and the correction, the sign correction I explained before, and then you just take this. So these are only ingredient in the proof. So not so complicated. But I just want to say this. So d of xi1 xik plus -1 to I -1 and this xi1 and d xi I xi k plus so I don't know how to what is a good way to write it, but 1 plus wait. Yes. Maybe it looks like this. Okay, so xi I and xi I plus 1 and xi k, right? So there are only k minus 1 entries. So here I have this. Or maybe you call prime here, right? Because I just move this. Yeah, this is equality, but now I just do this, and then this one is equal to 0, right? And this one very similar to the infinity relations. So infinity relation is the following. So mk1 of xi1 mk2 of say xi I xi I plus k2 minus 1 xi k, and then take here So just take a sum of shifted degrees in front of this mk2, and then sum them up, and this is equal to 0. So this is infinity relations, and this one is very similar. But how it's similar? Because so here somehow you take something and then apply this, so you get something. So this is one operation, and then apply d, right? And here I apply d, and then do this operation. Here I have this thing, and then this operation. So something very looks similar. Not really the same. And the sign appearing here also somehow similar. But not really related, but somehow you may just observe the sign here. And so this one is not really infinity relations, but what I want to say is that this infinity relation is actually, for MK, because MK is actually define this kind of stuff. So certainly, if we have a relation among MKs like this, and then this one should be also, iterative integral should be also satisfy something. So this is just this. But more precisely, what I want to say is the following. Somehow here we have this d here, and here we have this. Okay. So what is this? This xi1 d xi k. Right? So then here I have a map, something like xi I minus 1. So this is actually the sum of shifted degrees. So this star I minus 1 is a shifted degrees of xi1 xi I minus 1. So this is a kind of Leibniz, cosine sign. And the second one, so now I just write it. This is first, and then I have xi1 this, and then the shifted degrees of xi1 to xi I minus 1 is the same like this. This is again the cosine sign, and here I have this minus 1 to the power xi I prime and xi I plus 1. So in fact, if you have DGA, you have a exterior derivative. Okay, so if A and D and maybe product is DGA, and that is D square is equal to 0, and if you consider DAB is equal to DAB plus ADB, and then associativity is this thing. I think I already mentioned this some time ago. And then I have M1, say M1, maybe I just put the same like D. But M2, so last time I may put it this way. But this one really, there are several choices. So I think last time I say this, right? I do this. And then you just compare, you just consider the corresponding relation here, and then here you have M1 square is equal to 0, and second one is M1 and M2 AB plus M2 and M1A, B, plus minus 1 A prime of M2A, M1B is equal to 0. So this is actually exactly correspond to this, if you put this. And the third one is M2AB, C, M2 plus minus 1 A prime of M2A, M2BC is equal to 0. Okay. So last time I said this. But this sign can be also the prime. So this is okay. This is okay. But if you consider another one, like let M, maybe better to write M2 prime of AB is equal to minus 1 A prime of AB. So I just change this one to this one. But still this condition holds because M1 square nothing to do with this M2, so therefore it is okay. And second one, M1 appear once here. For each three term, M1 appear here, and M2 appear here. So therefore, if you replace this one to this one, you just change this formula, just multiply by minus 1. So therefore, if the formula holds for this, and then formula holds for this, right? And this one, the same thing. So here you have M2, it appears twice. So therefore, if you change from here to here, actually this also holds. And so last time I said that this is a way to get infinity algebra from DTA. But you can also get infinite algebra from this. And what I want to say is that, so here actually we have this. So this is exterior derivative, and this is actually this operation. So somehow you have DTA, and then you just look at it as an infinity algebra, and then you can just do these sort of things. But this is so-called, this well-known things, this kind of, yes. So this is just, maybe I just stop here. And, okay, so I have already, so I already spoke 1 hour. Okay, I think I plan to prove this, but maybe too much, so therefore I just stop. Okay. So the next thing is somehow, yes, I have to explain a few things which I didn't really did last time. And but maybe better to speak about examples because that may be more interesting. Okay, so. So actually, so what we did is this, right? So here I have this x x, and here I have this moduli space, and then this is a picture which I used before, and today I used to be the different picture. So somehow I just define some differential form on that space. Right? So I don't know. So maybe I may. So this is not really a correct way. So maybe I may just tell it later because, and also, maybe if I have a loop space, and then I also have a evaluation map 0, and then also have a map to this, like this. And so for construction of infinity algebra, I pick up some different form here, and then put it back, and then push out like this. And so this one is actually pushed out at this. And this one is F1 than Fk. Right? So here, F1, Fk here. And F0 is here. And so, as I said, you can just do these iterated integrals, but also you may pull back different form here. That means somehow, so our operation is somehow omega dot x tensor k goes to omega dot, sorry, maybe L. But anyway, this is all Lagrangians, but anyway. So like this. But if you have a pairing, then you can think of it as a map like this, right? So differential form here is somehow pull them back and push out, and also pull back this and wedge, take a wedge. And here, if I want to do the same thing, I just pull it back, and then integrate over here. So iterated integral somehow gives you something here. So in other words, actually, this moduli space somehow gives you chain in the loop space. And so similar to this one, actually, we can also cook up some differential form on the loop space, and then try to integrate over this chain. So you have a chain because differential form is defined by this, right? And then you have some differential form here. So if you have a chain, maybe linear combination of singular simplices, and then you can pull it back. You can think of this differential over here, and then you can integrate it, right? So then I just pull back the differential form from this side, and then do this. So therefore, if I consider this integral over the moduli space of the differential form like F0 star of psi 0, and then this sort of stuff. So this one is something like this. Maybe better to put it opposite side. I take this psi 0 and put it back to the moduli space, and then I have this differential form. No, sorry. I put it back, and then take this iterated integral, and then take a product, and then make an integration over this. Or maybe you first apply this and then do this. I think it's something like this. So this iterated integral somehow gives you some differential form of the loop space, and then this moduli space of border stable map gives you a chain in the loop space. And then if you want to pair the differential form coming from iterated integral and this chain coming from moduli space, then that is somehow given by this. Is it? Okay. Not so, because this one is, compactification is different, so therefore a little bit. So somehow this one actually, if you take it's a pair of the mapping and domain and map points, and then if you look at the you just restrict the mapping to the boundary, and then you have a chain. You have a element, a loop space with Lagrangians, and then this one actually also gives you a chain in the loop space of the Lagrangians. Yes. Because modular space has a mapping to this. Sorry. Because modular space, so here I have say disk, and then this, right? So therefore you can just take a boundary loop. So therefore you restrict it to the boundary, and then you have a chain in the loop space in a sense. And then you Is it okay? Maybe something you may. Yeah, maybe I should say such a thing when I explain this, but maybe. Okay. So what else? Yeah, so examples. Yes. So this is the part I wanted to speak first. So this is iterative integral stuff, and then the second part is actually examples of computation of this potential function of x, or maybe potential function of this. Maybe just today I may just give you maybe one or two, and then okay. So last time I already explained what is CP1, and CP1 is this one, and then this is the momentum map. I denote always by pi, and then if it's 0 and this is 1, right? And then the potential function of CP1 of y is equal to y plus t over y. So this is so this one corresponds to this PO LU is equal to yu tu plus t1 minus u of yu. And if I'm here, and then the area here is somehow 1 minus u. No, area here is u. Sorry. Area here is u. And area here is 1 minus u. And then these actually appear here. Somehow yu here and here inverse yu there. Because if you look at the boundary of the holomorphic disk, then the boundary is oriented in the opposite way. So therefore they appear as inverses. Because in the element of homology, certainly, yeah, this is just a negative. Yeah, these are related by multiplication by minus 1. But then we took exponential things. So therefore, for y actually, this is just yu and 1 over yu. And so this is okay. And then the next thing is certainly CP2 we also discussed, but maybe I will come back sometime. And so the next thing is product of CP1. But symplectic form may be not exactly the same. So here, maybe I have omega here, and then here maybe, I don't know, lambda times omega. maybe lambda is non-zero constant. Yeah, certainly something like this. And then, so this is actually Fano case. So there are 4 basic or meridian classes. Because here I have the CP1 cross CP1. And then the momentum map is something like this. The image of momentum map is like this. So this is 1 and, 0, 1, lambda, something like this. And so if I take one point from here, U1, U2, and then I have some torus here, then I have 4 basic things. That is something, yeah, so this is actually P1 cross P1. And then here I have S1, S1A, S1U1, and S1U2, something like this. And then certainly for in the case of CP1, so we have 2 disks, maybe D1 and D2. I don't know, maybe. So we have 2 disks. And this S1A. So the Maslov 2. So as I said, there are 2. So I may just denote by U plus and U minus, right? I don't know which one is plus, which is minus. But then here, actually, we have 4 of them, namely, I see, U is no good, so maybe W plus and W minus, okay? And then maybe I do also denote by A here, okay? So there are 4 classes, that is maybe W plus U1 and point, and W minus U1 and point, and the point times W plus U2, and the point times W minus U2. So we have 4 disks. No, nothing more. So therefore, our potential function in this case is equal to y1u, u1, y1u, yes, y1u of t u1 and y2u of t u2 plus t1 minus u1 of y1u plus t lambda minus u2 over y2 of u. So we have 4 terms, and then the areas, yeah, so here this area is just u1, and this area is 1 minus u1, and this area is u2, and this area is lambda minus u2. So we have these 4. And if I want to write PO of this CP1 omega times CP1 lambda omega, and then this one is equal to y1 plus y2 plus t over y1 plus t lambda over y2. And in this case, it's very easy to compute the critical points because they are separated, right? Here you have this only something appearing y1, and then here you have something only appearing y2. So therefore, the critical points of this thing is just a product of critical points. So So this is the following. So first one is maybe t 1/2, and then t maybe half of lambda, and t minus 1/2, and t half of lambda, and here I have t 1/2, and t minus lambda here, and then t minus 1/2, and t minus lambda 1/2. So I have these four. And yes. And it's also important to look at the values, namely critical values. So maybe later I may come back to this, but you may consider these critical values. Maybe I will explain it later. And then the next example is maybe a bit more interesting. So this is CP2. Going to this. So this one I already computed, right? CP2 is equal to y1 plus y2 plus t y1 y2. And in fact, in this case, this potential function of the Lagrangian is actually given as follows. This way. So this is actually I already explained. And then the critical values, critical points is actually the cubic root of unity times t 1/3. Right? Zero, 1, 2. So we have three solutions. So now I consider 1-point blow-up of this. So 1-point blow-up certainly in symplectic, equivalent symplectic geometry, it is actually chopping off some corner. So we just chop off this corner, like this. And so here it is 0, here this is 1, and then here I have maybe 1 minus alpha, and here 1 minus alpha, alpha 1 minus alpha. So this one is alpha 1 minus alpha. Okay, so this way. And certainly we can also write the potential function of this guy. So the potential function of this manifold is equal to y1. y1 is the same this way, and y2 is also the same. And this one is also the same. So we have this term. But in the end, we have the other ones. So that is yt 1 minus alpha over y2. So this is the potential function for one-point blow-up. So this one is also Fano, so therefore we have only basic classes contributing to this. Okay. Okay. So
last time we defined the PO of Lagrangian products, but what is the PO of open space?
yes, so I actually last time I actually also defined this. So maybe just remember the argument. So I have this PO LU. At the beginning, it's in the variable x1 xn, right? So B is an element, just a sum of xi and ei. And then I change variable, so yiu is exponential. This is usually exponential of xi. So this is actually sum of k, 1 over k factorial and xi to the power k. And so this one is equal to this PO LU and y1u, ynu. So this I explained, right? And now I introduce new variable, yi is equal to yiu times t to the ui. I introduce this new variable, and then just write down this thing, and then this one is, and then this one is doesn't depend choice of u. So this is just a change of coordinates. And so maybe it's better to write this one too. Maybe yeah. So this 1 minus u1 minus u2 and y1u, y2u plus t to the minus 1 minus alpha minus u2. Yes, u2 over y2u. Okay. So now I just compute its critical point, this critical point of this guy. And then you can see where it appears. And then you can see which torus fiber carries some B so that Floer theory is non-trivial. Okay. So now I just do these things. Okay. Yes. So, okay. Because somehow writing y1u, y2u all the time may be a bit too much.
Is there some TU1 missing?
Where?
The leading for you, the Y1.
Ah, sorry. Thank you. So even though I have to write it as yiu because yi is this one, but let me write it y1, y2 in this computation. Is it okay? Maybe I don't really like this, but what is a good letter for this? X, Y, Z, W are used for some purpose, and so I don't have any nice coordinates. So sorry. So okay. So maybe I just denoted it by this kind of. So just I want to write it in this way, okay? And then I want to consider So I want to compute this, and then this one is certain TU1 here, and then this one never happens, and but minus, and then here I have this y1 square and y2, and t1 minus u1 minus u2 plus, minus t1 minus alpha minus u2, and then y2 square. So this is correct? No, sorry. Maybe y1. Sorry. No, I don't have this. Sorry. I don't have this. I have only this. Yes. Sorry. Yes. And then I do this for y2. And then here I have a tu2 minus here. So t1 minus u1 minus u2 and y1 and y2 square, and then minus of y2 square and t1 minus alpha minus u2. Okay. So I want to find a critical point. So therefore I want to solve this equation. And the first one is okay. So the first one is this. So tu1 is equal to t1 minus u1 minus u2, and here I have y1 square and y2. Okay. But I want to find a solution so that this y1, y2 belongs to lambda 0 minus lambda plus square, right? Because this one is this yiu. This is actually a sum of exponentials, this is exponential things, and xi is in lambda 0, and then this yiu actually coordinate here. So therefore, we only consider this element from here. So if there is a solution like this, then automatically we have a constraint for u1 and u2. So that is this. So u1 must be equal to 1 minus u1 minus u2. Just taking variation of this. So this means that variation of this y1 is equal to variation of y2 is equal to 0, right? So this takes the exponent of the lowest order term, and then you have this. And so here it starts from constant term, and so therefore this is actually invertible element in this lambda 0 minus lambda plus, and so the variation of this one is 0, and so therefore variation of this one must coincide. So taking variation, you have this. So then I may put u1 by s, and then u2 must be 1 minus 2s. Yes? Okay, so this is from the first equation. And then look at the second equation. Again, we take a variation. So variation of those are all 0. So here take a variation of this, and then this one is equal to u2. Take a variation of this, it's 1 minus u1 minus u2. And this variation is actually 1 minus alpha minus u2. So if those values are distinct, then no way to get 0 here. Because this is actually the lowest order terms, and if so you take the smallest one, and then that smallest one cannot be killed by other ones. So therefore this one implies at least two of them must be the same. So I just wanted to say this sometime. So okay. So in order to have this solution, yeah. So if there is a solution y1, y2 belonging to lambda 0 minus lambda plus square for this 1 and 2, then from the second equation, I have four cases. So case 1 is u2 is equal to 1 minus u1 minus u2. And maybe the other one, 1 minus alpha minus u2, is bigger than this. And second case, u2 is equal to 1 minus alpha minus u2. And then it is less than 1 minus u1 minus u2. Okay. And third case is these two coincide. So 1 minus u1 minus u2 is equal to 1 minus alpha minus u2 and less than u2. Okay. And case 4, all three coincide. So just u2 is equal to 1 minus u1 minus u2 is equal to 1 minus alpha minus u2. Okay, so there are four cases. And for each case, we can just do some computation. I don't know. So is it okay to continue? It may take some time, but or maybe just give you some conclusions. So the first case, because if I can say this, then it's better. But in this case, actually, we can see that this S is equal to 1/3, and alpha must be less than 1/3, and the solution is actually y1, y2. Solutions are actually congruent to theta 3 k11. So therefore, three solutions over this 1/3, 1/3 in the momentum polytope P. Maybe I may tell you some story later. And the second case, in this case, alpha must be bigger than, yes. In my computation, yes, alpha must be bigger than 1/3, and S also bigger than 1/3, and in fact, we have four solutions over this for 1 plus alpha and half of 1 minus alpha, also this. And third case, in this case, u1 must be equal to alpha, and S is actually just 1/3. Maybe this is not so important. And I have one solution. Sorry. In this case, S is 1/3. And yes. Sorry. S is equal to u1, right? So S. I put S somewhere. S. Here. Here. S is u1. Okay. S is u1. So therefore this is u1, right? So is this 1/3? And so here it has a one solution over alpha 1 minus 2 alpha. Okay. The last case, in this case, U1 is equal to alpha and U2 is equal to 1 minus 2 alpha, and alpha must be equal to 1/3. And we have 4 solutions. Yes, so we have 4 solutions over this one, 1/3, 1/3. I think so. Maybe I have to explain what it is. So yeah, the computation is the following. So you just look at this, and then you just try to see the leading order term, the condition that leading order term vanishes. In this case, actually, here you have this relation. So therefore, you may just write maybe y2 as a y1 square times y1. No. Y2 is equal to t something over y2 square. And then you plug in this into this equation. So therefore, you have a algebraic equation in y2. Okay? And then you look at the lowest order term, and then just try to see whether such a thing has a solution or not. In the lowest order term, I mean the coefficient lowest order term. And in this case, this equation, lowest order term, so just a complex valued equation, and that has a solution. All the solutions are simple. Then those solutions can be extended to a solution on this lambda 0 minus lambda plus. And this is actually a consequence of kind of so-called Helmholtz lemma. And for complete variation ring, and you have such a thing. And so you just try to solve it, and then leading order term, the lowest order term, and then you just check there are so solutions, and then automatically extends to the solution on the lambda 0 in the lambda 0 case. Okay, so what is the conclusion? The conclusion is the following. So here, this 110 stuff, and you can see that there are some conditions that this alpha is bigger than 1/3, or alpha is less than 1/3, and so on. What does it mean? So alpha is a height, right? Alpha is a height from above. But anyway, so here you have this. This is 1 minus alpha. So if alpha is less than 1/3, so very, very tiny in a sense, and then we have several solutions. So this number 1 gives you 3 solutions. So namely here you have 1/3, 1/3. So here you have 3 solutions. Other point has no solutions. Here, So sorry. Here you have solutions. And then I have another possibility, that is this one. If in number 3, case 3, and then you have 1 solution. So if alpha is less than 1/3, you have such a thing. So what does it mean? So this one is in fact the point like this. This is a point like this. This is a point. Sorry. This picture is not good. This picture is not good because 1/3 is maybe very bad. Okay. So 1/3 maybe somewhere here. Okay. And then here the point is alpha, 1 minus 2 alpha. So here. So in this case, I have here over here, we have three solutions. Here I have one solution. Okay. And next, if alpha is 1/3, namely 2/3. In this case, if you look at this expression, alpha is 1/3, and then this is exactly 1/3, 1/3, right? So here, if I chop it off here, and then this orange one and white one actually coincide and becomes 1 point here. So 1/3, 1/3. And here I have 4 solutions. So this is the case. If alpha is 1/3, you have 4 solutions. Yes. Okay. So now I already mentioned this 1 and 3. And then this one is the case alpha is equal to 1/3. And then the remaining case is this. Like this. So it's 1 minus alpha. Okay. In this case, they are not, this 1, 3, 4 not applied, because if 1, then alpha is less than 1/3. Case 3, alpha is less than 1/3. Case 4, alpha is 1/3. So therefore, they cannot be applied this case. Only second one applies, second case applies. And then in this case, we have a point. So 1 over, so this is a point like this. So you take a midpoint here. This is just half of 1 minus alpha, right? And then you just look at this. And then this point is actually, yes, to 1 plus alpha and to 1 minus alpha, right? Because this is a x plus y is equal to 1, so therefore this one, right? And then this is actually the quarter of 1 plus 4 alpha. So that is actually midpoint here. So this is a point for 1 plus alpha and 2, 1 minus alpha. And then over here, we have those 4 solutions. So in this case, we have separate 2 points, and then number of critical points lying over this is actually 1, but here we have 3. And here they actually merge to 1 point, and then they actually come to the same point, and so therefore we have 4 critical points. And here, after that, actually this one no longer a critical point, but this critical point actually moving to below, and in fact this one still have 4 critical points. So this is just this sort of computation. Sorry. Like this. So always the Euler number is equal to 4. So why is this? Maybe, yeah, I also want to tell you one more thing, but before that I may just mention this. So the last time I said the following, so in the final case, and in fact in general it is also true, but the quantum cohomology of this thing is isomorphic to the quantum cohomology described by Bacherev. And this one is isomorphic to this lambda z1 zm modulo these linear relations and the quantum Stanley-Reisner relations, right? And this one is actually isomorphic to so-called Jacobian ring. So this lambda y1 plus minus 1, da 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 yn plus minus 1 over this yi dpo dyi. This sort of idea. Okay. Yes, this sort of idea. Okay. So this is, what is this? So this is actually a ring of functions of the common zeros, right? That is actually critical locus. So I have here, sorry. I have here so this is a function, and then I consider this dpox and dyi, because here yi is invertible, so therefore even multiplying yi doesn't really change. So this is a ring of regular functions on this. So therefore, if you consider this, okay. And also I gave a name of this, and I gave a name of this. This is actually so-called Jacobian algebra of this function Pox. Okay. So I have a Jacobian algebra of this thing, and then consider all possible maximal ideals. In other words, I consider all unitary homomorphism to this lambda. So this is unitary ring homomorphism, like this. So this is exactly the set of maximal ideals. So close the points. And so this one is exactly same as the critical point locus of this kind. Okay. So the number of critical points is same as number of maximal ideals. And so here you have this quantum cohomology. They are actually ring isomorphism. So therefore this one is same as And so if all the zeros, all the common zeros are non-degenerate, namely this ring of regular function actually decompose into a copy of lambda, and then you just count the number of unitary ring homomorphism. It's just the number of factors. And if you look at this is exactly the rank of this one, right? So therefore the number of critical points is actually same as the sum of Betti numbers of the quantum, the toric manifold. And this is okay for Fano case using this batchless quantum cohomology. Non-Fano case, actually this is not true and descript, but nevertheless we have a variant of Jacobian ring, and so this one is also isomorphic to certain version of Jacobian ring. So this is not really this. And so finally I just want to mention such an example, and then maybe today I just stop. So this is also quite standard example, and maybe you already heard of it. So another example is this Hilbert surface. Maybe Fn. Okay. N, yeah, okay, Fn. So this one is a projectization of of this O times OP1 times OP1 and so you have a P1 bundle over here, P1 bundle of P1, and then this one. And then if you look at the momentum polytope, certainly it depends on the choice of basis of the lattice, but it somehow looks like this. And then, then this one is singular. So therefore, I have to chop off the corner of this. And then I consider this. This is the momentum polytope of this. So let's consider the naive one. So suppose, so this is actually, if n is bigger than or equal to 2, then not fun. So, and if n is n equal to 2, then it is not fun, but not so bad. Namely, the negative of this canonical bundle is still so-called nef. But if n is strictly bigger than 2, and then no longer this. So in this case, you may wonder whether those stories actually worked or not. Suppose that the same argument, so same conclusion holds. Same conclusion holds. So actually what I want to say is that the same argument doesn't work. So suppose that the previous descriptions holds. And then I want to get a contradiction, right? So, yeah, I wanted to also talk about this, but maybe, yes. So in fact, what I wanted to say is the following. So here you have this Z1, Zm, they are toric classes. So therefore you have a Z1 plus Zm, that is first term class. Right? Z1 to Zm is the first term class here. And this Z1 plus Zm is mapped to here, then you get this potential function for Fano varieties. Okay? So here you have a C1. C1 corresponds to the potential functions. But now we only consider this is the ring of function with critical points. So therefore, the only information here is actually critical values. So critical values here, but those actually related to here because first term class is this Z1 to Zm. So the statement is that if you consider the quantum multiplication by C1 here, then consider the eigenvalues. Eigenvalues of the quantum multiplication by first term class, then that really coincides with the critical values of the potential functions. And if you have this, you can compute critical values and then compare with the eigenvalues of the first term class. And then you can just check such as in CP1 plus CP1 and those kind of examples. So that I wanted to mention, but I just stopped. And so what's wrong, right? So then I just do this and then stop. Maybe another paper. So in this case, this Fn is mapped to some polytope, and this polytope is written as this U1 is non-negative, and U2 is non-negative, and yes, minus U1 minus NU2 plus N is non-negative, and okay, minus U2 plus 1 minus alpha is non-negative, right? Something like this. These things. So therefore V1 is maybe 1, 0. V2 is equal to 0, 1. And V3 is equal to, okay, so V3 maybe here. So therefore this minus 1 minus n. And V4 is equal to 0 minus 1, right? And now I just write the potential function. So if the potential function is the form as in Fano case, and then this potential function should be the following form, like y1 plus y2 plus y2 inverse and t1 minus alpha, and then y1 inverse and y2 minus n and t to the power n. Okay, so just the same kind of formula. Let's suppose this is the case, and then this isomorphism actually holds. So here actually this is a geometric thing, and this is just algebraic description. And this isomorphism, yeah, it is in fact necessary to have Fano condition. But this Butterf, the description Butterf is actually isomorphic to this one. So this is actually okay for any toric manifold. And then this one is also isomorphic to this. So therefore this kind of description is okay for Butterf quantum cohomology and potential function in this form. Okay, so that's what I said here. So suppose that the previous description holds. That means the potential function is like this, and this one is isomorphic to this. And then what happens? Okay, so this, and okay. So again, I have to consider this partial derivatives, and yes, so maybe this one may be a little bit, yeah, messy, but maybe without really mentioning this, maybe it doesn't really make sense. So I just want to tell you the story. So I just do this dd(y1) of this potential function, and then this one is equal to 1 minus y1 in y1 square and y2 minus ntn, and this dd(y2) is equal to 1 minus n y1 minus 1 y2 minus n minus 1 and t to the power n minus y2 minus square and t 1 minus alpha, something like this. Okay. So somehow, yeah, okay. And then the first one certainly tells us that y1 square and y2 n is equal to t to the power n. So maybe, yeah, I just want to erase, discard this variable y1. So therefore, maybe I just put y2 is just z square, and then y1 is equal to maybe plus minus and z to the power n minus n and t half of n or something like this. So something like this. Okay. So just put y2 is equal to z square, and then so then y1 should be plus or minus of this thing. And then just plug in this to this equation. All right. And what I have is this. Okay. Then I have the following. So something like plus minus z to the power minus n and t half of n and z to n minus 1 and z to the power fourth minus t1 minus alpha and n t n equal to 0, something like this. And so now I pick s as a variation of this variable z. And then, so we have actually again 3 terms. So there are 3 cases. In order to have this equation has solution, so you have 3 terms, and then look at the lowest order term, and then 2 of lowest order term coincide, and then the another one is at bigger or equal to that one. So therefore, we have this, and so there are 3 cases, and then case 1 is actually n plus 1 times s equal to n minus 2s plus 1 minus alpha, which is less than half of n. And case 2, maybe I also have to consider other case, but anyway, so n plus 1 of s is equal to half of n and less than n minus 2 s plus 1 minus alpha. And in fact, in this case, no such case appears. This is just some computation. And in this case, we have solutions. In this case, actually solutions over s equal to, yes, over variation, solution, so the solution z, so that variation is equal to quarter of 1 minus alpha. Quarter of 1 minus alpha. Okay, that's okay. And then the third case, maybe I need to consider another case, but anyway, here is n minus 2s plus 1 minus alpha is equal to half of n and less than n plus 2 times s. Okay. And in this case, we can find some solution, but in this case, there is a solution, z, but the variation of z is actually bigger than one half. It is actually bigger than half of 1 minus alpha. So this kind of computation is, yeah, as I said, I just look at the leading order term and then just check whether such a thing has solution or not. And in this case, you have some solution. And this is a problem because now you remember y2, so this one implies variation of y2, yeah, is equal to 2 times variation of z, which is bigger than 1 minus alpha, right? So bigger than 1 minus alpha. That means the critical point is outside this polytope. And in this case, actually, we have more than 4 critical points because this one is extra. So if you want to include this, then no way to get this isomorphism, because this is rank 4, but this one is extra 1, so they are rank 5 or something. So therefore, and this one was first noticed by, I forgot. I should remember his name. Spielberg, somebody. And so this is example maybe first noticed by somebody. So, but anyway, so this is not the case. If n equal to 2, actually rank actually matches. And in fact, we can see that in that case, actually, this function. So if n equal to 2, the potential function is equal to, in fact, y1 plus y2 plus y2 inverse and t1 minus alpha and y1 inverse y2 minus n and tn plus y2 inverse and t1 plus alpha. So we have extra term. And after we computed by using the statement which I said before, the eigenvalues of the quantum multiplication by C1 is the same as the critical values of the potential function. We use that property, even non-Fano case, we have to establish such a thing first. And then using this, actually, we could find this extra term. And Dunyoru has another argument. He actually used this wall crossing type argument to really get this. And this is okay for F2. But F2 is certain very special type of singularity. It has, it's a kind of resolution of singular F2, and singular F2 has A1 singularity. And so you may just take a resolution, and then you get this, and so you have this. But how about A2, A3, and so on? I forgot up to something. It was computed by Conan and his students. Kokwai and Shukyong and Conan, they computed it using kind of, so it's a counting of stable disks, but somehow they actually consider extended to a certain rational curves, and then using as a method to compute this, the Gromfried invariant type stuff. So now the argument is okay up to something. And after that, somehow, I don't know, I haven't really read the paper, but a student of Kendley actually did it for any AN. But a local computation, not a global one, but local. So anyway, so this is we have an extra term here. So therefore, potential function of F2 is not same as potential function of this one. But we have a bulk deformations. And after bulk deformation, actually we can kill this term. And so therefore, actually such a thing appears as a bulk deformed potential function. And so what we have is that if you consider bulk deformed quantum cohomology with certain bulk class, and that is in this F2 case actually isomorphic to this. And so, but also this one should be excluded. So we have a technique to exclude such a thing, namely not just this idea, but somehow take the closure of this idea with respect to t-adic topology. Maybe I may speak it maybe next time, next Saturday. So somehow, taking closure somehow, making this one bigger, and then certainly less candidate. And so, okay, so that's all.